In our investigation of exponential relationships, we're going to use this table of values to try and define a couple of things about exponential relationships. So please remember that all exponential relationships are written in this format, where we've got y is equal to a times b, which is the base of the exponent, raised to the exponent x, so whatever that happens to be. So in this first example here, we have the equation y equals 4 to the exponent x. So I'm going to substitute in my values for x and then write those out as fractions. So I'm going to do 4 to the exponent negative 3, and that's going to give me 1 over 64. Then I'm going to do 4 to the exponent negative 2. That's going to give me 1 over 16. 4 to the exponent negative 1 is going to give me 1 over 4. 4 to the exponent 0 will just give me positive 1. 4 to the exponent 1 gives me 4. 4 to the 2 gives me 16. And 4 to the 3 gives me positive 64. So if I go and I want to graph y is equal 4 to the x, then a couple things I need to be aware of as I'm going through and graphing that. And I'll graph that here with the blue mark. So I know that my 0 is 1, 1 is 4, 2 is 16, and 3 is somewhere off the chart. Negative 1 is 1/4. So when excuse me, x is equal to negative 1, y is equal to about 1/4, and then down, and then down. So if I graph this, I end up with a line that looks something like this, and it just keeps going up. Okay. So now what I'm going to do is I'm going to add in, so in this particular example, this is also equal. This is also equal to 1 times 4 to the x. So the a value in this first example is actually 1. Here, our a value is actually 2 in this second column. So this is our a value. This is our b value. So in this case, I'm going to take my a value. I'm going to go through and I'm going to multiply the same piece of information. Okay, so I'm going to actually do 2 times 4 raised to the exponent negative 3. Okay, and that's going to give me 1 over 32, okay, which is half as big as just 1 over 64. Then I'm going to do the same thing over here. I'm going to go 2 times 4 raised to the exponent negative 2. That's going to give me 1 over 8. If I do 2 times 4 to the exponent negative 1, that should give me negative 1/2. If I do 2 to the exponent 0, that should actually give me 2. If I do 2 to the exponent 1, that will give me 8. 2 to the exponent 2 will give me 32. And 4 to the exponent positive 3 times 2 will give me 128. So now what I need to do is I need to go back and actually graph this. So again, I know that at the 0 mark, the y coordinate is going to be 2. So now I'm going to put this in there. At 1, it's 8. And at 2, it's actually up here somewhere at 32. at -1, it's 1/2. And slightly above. So I'm going to end up actually with an exponential curve that is rising at a steeper rate than we have in the original. So when the a value is increased, the curve, or the steepness of the curve rather, is radically increased as well. So what happens though if the b value is less than 1? So in the first two columns, we've seen that our b value is 4. So it's a number that's bigger than 1. And in the next two examples, we see that in fact the b value is less than 1. In fact, it's a quarter. So if we go through and we discover what that's going to end up looking like, we see that when we have the equation y is equal to 1/4 raised to the exponent x, then what ends up happening, excuse me, is if I do 1/4 raised to the exponent -3, I actually get positive 64. If I do 1/4 raised to the exponent of 2, that's actually going to give me 16. If I do 1/4 raised to the exponent -1, that gives me 4. And 1/4 raised to the exponent 0 is going to give me 1. And then, interestingly enough, as I go into positive numbers, 1/4 raised to the exponent 1 gives me 1/4. 1/4 raised to the exponent 2 gives me 1 over 16. And 1/4 raised to the exponent 3 gives me 1 over 64. So I have the same numbers, but they're now suddenly in reverse order. They've been flipped. And so what this means actually is that if I were to graph this, I would end up with, I wish that didn't happen. So if I go through and I attempt to graph this, then I end up with numbers that actually increase quite substantially. Okay, so, and then at 1 it becomes 1/4, and then even less and even less. So if I graph this, I have the same curve, but now it's going in the other direction. Okay, so again, let's see what happens if we change the a value. So on this particular graph, we'll change the a value from being 1 to 3. We'll raise it up. So I'm going to choose a different color, and I'm going to go through, I'm going to do the same process here. So I've got 3 times 1/4 raised to the exponent -3. That's going to give me 192. If I do 3 times 1/4 raised to the exponent -2, that gives me 48. If I do 3 to the exponent 1/4 raised to the exponent -1, that'll give me 12. If I do 3 to the exponent 1/4 raised to the exponent 0, it gives me 3. And then if I continue on, I'm going to end up with just even smaller fractions as I do my multiplication. So now let's go through and attempt to graph this particular relationship. So we've got 3, 12, and then somewhere way up here. And then it goes up. So again, some interesting things that we can note right off the bat here is that if you compare the graphs, you see that whatever the a value is, in this case the a value is +2, that actually happens to be the y-intercept. Here, the a value is 1, and the y-intercept happens at 1. Again, we've got the a value of 1 here. That means that you've got a y-intercept of 1, and here we've got a value of 3, and so the y-intercept is made 3. Okay, so that's one thing that we can tell right off the bat. The other thing that's really interesting is that if you look at the b value, whenever the b value is bigger than 1, we notice that the graph increased from the left to the right. Okay, so it increased in value. So we can say that it increased in value. However, when the b value was between 0 and positive 1, it actually decreased in value. Okay? The curve was a decreasing slope. So the y-intercept for each of these graphs is given to us right in this section. Okay, we saw it digitally. We saw it on the table of values. We can also see that the y-intercept is right there. And what's really key about the y-intercept is that the y-intercept is equal to the a value. Okay, and so you can get that from the equation just by looking at whatever the a value is, or you can look at the graph and you can see where the y-intercept is on the graph. So the next question here that we want to try and ask is, why don't any of these graphs happen to have a y-intercept? And the reason they don't have a y-intercept is because every time that you go through, you actually are and you raise up the power, it never actually gets to 0. Okay, so if you decrease the exponent, so in the first example, on the left-hand side of the column where we have y is equal to 4 to the exponent x, if I go negative with the exponent being -2, -3, -4, -5, -6, -1000, I'm always going to end up with a fraction. I never get to 0. So even though the number is remarkably small, it never actually gets to 0. Okay? So why don't these graphs have an x-intercept? And the reason is because the line never gets to 0. Okay? The line or the curve never gets to 0. It just continues to get smaller and smaller and smaller and smaller, and it approaches 0, but it never actually gets to 0. So I think we'll stop there for a moment and then continue on.